All right. I have a couple more homeworks. Read, we already talked about that. Rolando, looks like you had, no, fail, let's be nice, okay? Kindness. Rolando, I think you did about half.
Yeah, that's what I thought. I felt like
Yeah.
I underthought this.
Well, no, just notice that there's other questions, right?
Yeah.
Specifically talking about how everyone else would have fared.
Yeah,
I can-
I don't mind doing that. I only focus on myself.
So, yeah, sure. Trinity, sorry.
My cute little $2.
It's 9, okay, it's substantial for some people. Unfortunately, I don't have a very good bet today. So we could, we could have fun, we could revisit one that we think we maybe understand already. But as I mentioned, we're gonna be moving more in the direction of the mathematical part of this mathematical methods class. And less in the have fun part of the mathematical methods class. With strike at the very beginning and then campus getting rained on, I think we're running a little behind where I wanted to be at this point. But we have some flexibility. If you look at the timeline, I always know that I never move anywhere as fast as I want to. We were talking about properties of, or talking about distributions. So we were talking about random variables and how we construct these random variables. And you saw that we had created one for rolling 2 die, right? So we're gonna see today what are some things that you can do with distributions. And then hopefully, so Monday there won't be class because of President's Day. So on Wednesday, we will talk about the different types of distributions. And I'll show you, if you took Astro 4000 with me, I said the Poisson distribution, just threw it on the board and, expected you to already know it. And so now in retrospect, I'm realizing not such a good idea because you may have never seen that before. So we'll discuss what a Gaussian distribution is. We'll discuss what a Poisson distribution is and where these come from. And then we'll talk about them in the context of today, which is how do you use them to find information about the world, right? So some processes are Gaussian distributed. Why? What does that mean, right? And then my hope is that the week after that, we'll probably do a little bit more in the probability part before we head into something called statistics. So there are actually 2 fields. They intersect, of course, but statistics is the data collection part. Probability is the axiomatic theory, right? How do we construct probabilities to understand the world versus statistics being how do we view the world and infer what the likelihoods are. Make sense? Okay, any questions before we get started? No questions. Have you seen the homework?
Yeah.
Ooh, who hates homework? Any questions on the homework?
I'll say for office hours.
What's that? Just saving for office hours? I think Rolando might be the only person who's actually ever come to office hours, so. Haven't needed help yet. Homework's been super easy, bro. That's good. I'm glad to hear that. But if you guys, I said this to my 3300 class as well. If you need different office hours, or if you find yourself being like, hey, I just need 30 minutes on a Thursday morning or on a Friday or something, we can adjust it as necessary. Is that cool?
Yeah.
Okay. Only do 2 of the problems unless you feel like really motivated. You do 3 of the problems, I'll be like, wow. I won't get you anything, but I'll be like, wow, okay. And then if you have any questions about the homework. So let us talk about. Let's go. What are discrete random variables?
Discrete random variable.
A discrete random variable X.
Oh, it's a PHYS function. Where it has a value.
It's not continuous.
Okay, hold on a second. Let's walk backwards.
Here.
Discrete, not continuous, good. What's this word? Random variable.
Basically a condition that you set X to be, sorry. A condition that you set X to be, like within the sample space, like the sum of 2 die or.
Okay, I like most of those words. I'm just gonna change one of them. Condition to event,
Event.
right? So I'm interpreting it as all the possible outcomes, all the possible events, and they will have discrete values. Okay, now you'll notice that, you know, if you roll 2 die, or maybe you roll 1 die and the odds of getting an even number, that's not an integer. So you might say to yourself, wait, does that mean that this is not a discrete variable? Do the values themselves have to be integers? No, why? It just has to not be continuous, and in particular, they can't be integers, because you're stuck with 2 integers, 0 and 1, and all probabilities must be bounded by this, right? So they can have discontinuities without being integral, right? Okay. So, we said some stuff about, you know, we had some balls that we were drawing, and we had a continuous distribution. So let us write something like this: the probability of X being less than capital X, less than or equal to X plus dx. Okay, and so everyone who's a fan of calculus will remember this type of terminology. What's that? Yeah, it looks similar to like the derivative type stuff.
Yeah.
So this would be your integral formalism, and we'll see that in a few seconds. This is telling us that it's continuous. Because if I use the delta here, then that would be, you know, sort of more like a sum, more like a discrete. So in fact, here we're going to be talking about continuous random variables. Okay. So let's write this in its form. So there's an f of x, we love that. And we're also going to say that it's over some small delta x. Okay. So in practice, it might look like this. And this is not a meaningful f of x. I'm just going to draw a random arbitrary curve where perhaps we're considering here the probability of x within x plus dx. Cool. Here. Well, you can barely see it, but we'll see. All right, we have the same rules that we had before that you will have for any sort of integral distribution. So let's say you want to consider the heights of individuals, as we did at the end of last class. We said that probably the heights don't go from -infinity to infinity. Right, they're probably bounded by something reasonable. So you might say something along the lines of, well, let's say L1 to L2, f of x dx. And let's say this is, we were talking about Americans over the age of 18 or something. And so let's put that at like foot, and let's put this at like 9 feet to be generous, right? So what would that integral be? So let's remember what this means. What does this mean? No,
The probability.
the probability of what?
The height being between one.
Right. So the probability of a person's height being between 1 and 9 feet. Like America.
Yeah.
Okay. So this is not some arbitrary function. And we have to remember that for this section. We're being very specific about this use of f of x. So this is our probability distribution function. And that we call. I know that's annoying. That's what it is. This was before the other PDF. This is ancient, okay? So what's the sum of the PDF for a continuous random variable over the entire range? Yeah, it's gotta be, right? Because that's how we normalize. We want it to be between 0 and 1. And similarly, if you had some other random variable that could go between minus infinity and infinity. Let's say this is a different one. What would you expect that to also be? Right? Also. Put arrows here. That we know they're not the same. Is that all? Is it good?
Oh, okay.
It could be delicious, but I don't know. Delicious PDFs. All right, so let's think about one more thing here, and we're gonna see most beautiful part of calculus, everyone's favorite part of calculus. So let's look at this. Let's look at the cumulative distribution function. Okay, so we define the cumulative probability function f of x. I don't know. Already wrong. Cumulative.
There's an M in there. It's human.
Yeah, you're on the right track, keep going.
No, there's a U.
That doesn't look great.
I know. All right, got really close, good check. All right, cumulative probability. Function. So what's that? What does it mean intellectually? What do we think about when we see that words in that order? I know you only saw them on Monday, but
All of them added up,
all of what added up?
some probabilities.
Sum of the probabilities up to that point x, right? So if I'm rolling the die, we're considering, I know that that's not a continuous distribution, but you might say, okay, let's take people's heights. What's the probability that you're less than or equal to 6 feet?
6, but.
In height, 6 feet.
Oh,
But what is the probable, not for you personally, right? We're thinking about a function. So the CDF would ask, what is the probability?
99.
Yeah, probably 80 or 90%, right? Does that make sense? Okay. And there are ways to think about this that are actually meaningful when you start to think about cumulative distribution function. So you might say something along the lines of f of x is the probability of x, x less than or equal to some little x that you're comparing to, which would of course be wherever you start the distribution to that location x, fu, du.
Sorry.
Reasonable, come on now.
I'm really tired.
Okay. Does that make sense? Okay. So this is actually going to be helpful, and we'll see this when we talk about different ways of understanding the distribution. For example, you might want to know what is the most likely probability. You might want to know what is the lowest quartile. What I mean by that is, what is the first 25% of the probability? Or the highest quartile. What is the highest 25%? And we'll see that when we talk about some of the things we can do with it. You see this integral formalism. So you see an integral over there, and you see the cumulative distribution function here, and the probability distribution function here. So what I can do, of course, is I can just butcher them, and I can come out with the relationship between them. So what's the relationship between f of x and this one? What's
Is
that?
f of x just like a section of the cumulative probability function?
Well, let's look at this. This is the big F, this is the little f. I do the integral to get this one. So to get this one by itself, I must derivative it, right? So we say this is the ddx of big F of x. Good. So that's the relationship between the cumulative distribution function and the probability distribution function. Okay. Cool. Everyone's brain is awake? No, thank you. Let's do a problem. Let's wake up the brains. I hate problems. Which were nothing homework. Okay. Random variable x has a PDF PDF f of x, where a to the e minus x from 0 infinity. Okay. And it's 0 anywhere else. It's only valid there. Okay. What is a? And what is probability
Is that a two after the second less than or equal to?
or did you that?
Yeah.
It's like one and like two, next number.
Yeah.
You get so many responses.
That's true.
Thanks.
I end up writing something with that. I'm going to my note then.
The value there is.
Can you do that? Is that possible?
Find value of A.
Mhm.
If you're asking from the answer.
Yeah, that would be reasonable, right? Have I given you everything on this board in order to do those things? The answer is yes. I warned you that this would become a math class, and thus it has. Okay, before you share any answers, we'll have a bet on this one. Oops.
Oh, you can do that. Correct. Yeah. How do I get to that? Just say crap. Quick, wait, just say my decision. How am I supposed to know? She's just saying crap then.
How are we feeling? We get it all? Don't share with your neighbor? Is there money on the line? Money on the line?
What are we betting for?
Just wait, you'll see.
$100.
$100 for what?
Yeah.
Yeah, right,
I
yeah.
bet I have the wrong answer.
Okay. Ready? Feel like you sufficiently answer that question? Did you get it close? Raise your hand if you started it. Raise your hand if you got A. Raise your hand if you got, what is the probability between 1 and 2? Okay, should we calculate what A is?
Yes.
Okay, anyone want to tell me what A is? Why is it 1?
You got one?
I did not get one.
So let's think about why that could be. Here's the probability distribution function, A to the EX minus 1. And I claimed here on some interval that includes all of the possible probabilities, so this would be 0, and this would be infinity. And I can replace this with A e to the minus x. Let's look at that. 0 to infinity of A e to the minus x dx. And we love integrating, especially exponentials, because you just get
Same thing.
same thing back. And so then you just apply it at the boundaries. And e to the minus x, when x is infinity, is 0. And e to the minus x when x is 0 is 1. And those two negatives cancel out. So this is equal to A. You say, wow, I didn't learn anything this morning. But I made this equal to 1 earlier, right? So this by definition has to be. Okay. Happy? All right, now can we do the second part? No, not as a group. So here's the question. Do you want to bet that this is the most likely location? That higher than 2 is the most likely location? Or that lower than 1 is the most likely? To do more math. Click, 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 click.
I realized my mistake. I put negative infinity for my lower bound
Hmm,
and I got 0 instead. So it was like, what the hell happened?
the other direction, yeah.
Yeah.
Hey, does anyone want the probability 1 to 2? Basically, going 1 to 2.
Like to answer it?
Yeah, I'm asking the question, which of these is the largest?
Hmm.
Interval 0, 1. Or 1, 2. Or 2, infinity.
Well,
I'll go to Dawn.
Put $1 on 1 to 2.
Are you gonna do a thing where you have it like pick something or is it just whoever answers right picks something?
What do you want to do?
I just want the right answer to get the money so I can. Or you do the card.
I was gonna do a card trick for 1 to 2, but we'll do both. You can double your money if you got the right answer. Got your wrong answer, you can single your money. You get this one.
You do the card trick for 1 to 2? Are you saying that?
Only for 1 to 2.
Is 1 to 2 the right answer then?
I don't know.
can I do from 2 to infinity for $48?
Oh, big money.
I didn't get what.
That's all I have.
All my numbers are trash. That one, that's different.
I didn't get the cards. I don't want that.
I don't get any of those really like that.
Ready?
I'll do $20 from 0 to 1.
$20 for 0 to 1?
Yeah.
That's the number that I've got in my computer.
Are we allowed to do the math?
I would hope so. That's why I've given you so much time.
Oh, thank God.
That's
Then
why you put your money on it, right?
can I switch?
$28 down, Don. What are you talking about?
Wait a second. Can I switch?
Oh my goodness. All right. Where do you want to switch to?
0 to 1 as well. I just
0
did
to
the math.
1. Okay.
Can I also put 20 on 0?
I do 100.
I'll put 50 on 0 to 1.
I hope we all lose our money.
Yeah, that's scary.
I hope there's like some weird trick.
That.
I will
He's like, actually, you haven't considered today is a Wednesday.
Win money off them. Why would you convince
I'm
them?
not winning away off them, I'm winning away off you.
Yeah, I help you train.
You want to quadruple your bet? Is that what you're saying?
Yeah.
All
so
in.
The rest of my.
$9?
Yeah. It's
Are we
just
good?
not-
All bets in?
Let me
It
try,
just
try.
bothered me that you're doing the card game for 1 to 2.
Yeah.
Doesn't bother me
No, because I already calculated one.
because it's the right answer.
All right, so let's answer this question. Okay, these are locked. Okay. So what's 0 to 1? It's the integral of e to the x 0 to 1. What's the integral of e to the minus x?
Negative.
Negative e to the,
and
yeah. Yeah,
Negative e.
To
to the negative e, or x, sorry.
Yeah.
Okay.
Yeah,
Another way of writing that, of course, is
oh, yeah, as a fraction,
x
yeah.
plus 1 over x. So this is the lower one, and this is the upper one. This one would be 0, and this one will be
I got the answer.
how much?
I think. the
Oh, I think it's
first
like that.
one-
It's like this, right?
I think it's the other.
No, that's.
You do
Oh, yeah, yeah, yeah.
Oh, yeah, it's the
the
top one
first
first.
minus the
Yeah.
second.
Very good. This is why we computer do the math. Okay, so what's this number?
0 plus 1.
So this is 1.
It's just 1, right? Yeah,
Right, this is 1 minus 1 over e. And what's,
yeah,
2.7.
so it's 1 over 2.7 or
it's
1,
like at nearly half.
1 over 3?
I was like.
A third.
It's 0.333. So this is probably 0.6,
Yeah, it's like, it's 0.63.
right?
I think hard to get the variance.
Right, that'd be fun, because this one's close to 0.2. And 0.2 you can do really easily with 5 cards. Okay, so what's this one?
Wrong.
Wrong, doesn't matter. Okay, 1 over e to the 1. That's about,
0.23.
all right, and this one?
Uh.
Who cares? This one's 0. 1 over e squared, what's e squared by the way?
1 over 9.
1 over 9.
Yeah. Because e 2.7.
I was thinking
Whenever I
about two.
see e, I think 3. Okay, that's just me, right? That's a physicist that like works with orders of magnitude. Hey, could you have guessed this? Instead of having to do all these disgusting derivatives,
I think you could.
you could have guessed this. So let's work on our intuition for a moment. This is the PDF,
Yeah. Yes.
right? And if we're looking at the distribution of probability, then it's the integral under the curve. Here's 1, here's 2. Which area is bigger?
0 to 1.
Okay, so some people won money and Trinity lost it all.
It's really sad.
Trinity, do you want to try and win your money back?
No.
No, no cost to win your money back.
Yeah, no.
All you have to do is select 10, Jack, King, Queen, or Ace, and be right, and you win 10 times your money.
Oh, it's a 1 in 5?
It's a 1 in 5,
90, and you can't lose, which is good.
but you have to get, that's right.
I'm nauseous.
What I'm gonna get?
What are you gonna get?
No.
All right, good.
What'd you say, Jack, King, Queen, or what?
Jack, Queen, Ace, 10. Oh!
Well, that was cool.
Okay.
I was gonna try and do that for people that 1 through 2, but no one felt like whatever.
I did the integrals from like 0 to infinity. No, and negative infinity to 0, and then like 3 to infinity.
So remember that from negatives, so this is the important part here, right? That negative infinity to 0 doesn't exist.
Okay.
Okay. So let's put a bonus bet here, so loses $1. And adds 10. Okay, does that make sense how we do this type of problem? So it's still mathing, right? It's just weird feeling. We can think about sets of random variables, particularly if they are not related to one another. So typically speaking, if you're Now, not every tall person in the room may agree with this, but IQ and height are not correlated, right, scientifically. I'm not saying anything.
Why would they be correlated in any way, shape,
Some tall people will tell you, right, tall people are better at everything, right, some short people will tell you that it's not true, right? I don't know what that has to do with. But we can think about the distribution of IQs, even if we ignore how bad that is a measure of people's intelligence. And we could say that their intelligence quotient, the IQ, is not related to their height. So therefore, you could have some distribution function, some PDF of heights, and some PDF of IQs. And you could then ask the question, well, how do I find a, 60 IQ over 6 foot? Right? And that would be looking at the joint probability function. So we won't go into these in detail, but they will just be, let's say you have some probability of x less than or equal to x, less than or equal to x plus dx. So that's the integral we talked about before, and that was our heights. But you can just simply add on to this the y's, where the y's are your IQs. Big Y, y plus dy. And just like you saw before, say in multivector calculus, you can just multiply these distribution functions together. So if one of them was f of x, then you'd have f of x, g of y, dx. Make sense? And that's infinitely standard. So you can add more and more probability distributions, assuming they're not correlated. We'll talk about covariance and correlation a little bit. Question about that? No. He's a perfect expert. Okay, so now we have to talk about the properties of distributions. And we're gonna learn a bunch of words. We ready then? I did. Sorry. My bad. We're gonna learn a bunch of words. Let's remember the scores. So when you think about the distribution function, we're talking about it in the context of these, how likely is it to find a height, or how likely is it to get a 2 or a red die or something like this. And we ask these questions in nature a lot too. Right? So you may have, has anyone taken quantum mechanics? Quantum mechanics?
E.
It's 2, 3, no quantum mechanics. Okay. So quantum mechanics is weird. Right? It's like a weird area. Because what we ask.
Facts. I said like true. It is weird.
Facts. All can know. So we think about a question like, well, where's the electron? Say, well, like you could probably tell that I'm present here. Electron, not so much. So you have to hit it with a psi, and that psi represents the likelihood of finding the electron in a certain region. That is a probability distribution function, right? It's a waveform. Similarly, we are going to be asking questions of probability distribution functions here. If you can remember to your quantum mechanics, if you don't have that, then this is going to be meaningless. But in order to find out something about the probability distribution function, you apply an operator to it. And we're going to do that same thing here, and we're going to have to define some words. So the first part here is we think about probability distribution functions in terms of averages or expectation values. So we have something that says expectation value. Okay, and you apply something that looks like this. That's an E for expectation value, okay? Of G of X. Some property of the distribution. So, some property. Okay, and this is the expectation. And in the case of a discrete one, you have a sum, and in the case, of a continuous one, you have an integral, and that would just be G of X multiplied by f of X. Similarly here, G of X multiplied by f of X, and dx. That doesn't look like anything, right? Does it ring any bells? I think almost everyone here, except for is taking computational though. So you will have seen weighted sums. So for example, if you can pull back the dust and the cobwebs and remember the RK4 or any of the integration schemes, sometimes you would take a value and you'd multiply it by a weight. And that would say weigh this one more than this one when you add them together. So this is a more important number than this one. That's called weighting the various data. So that one makes sense here, right? So you're saying, okay, apply to each of these values some weight. And the weight is the probability. What is the likelihood that you find that number, right? So if, for example, you think about the distribution of your rolls, so you have these two dice that you can roll, this is heavily favoring which number? 7, right? So you're more likely to have that sum weighted towards 7 than 12. And similarly, if you look at this distribution, which is the heights, you'd say, well, where is it weighted to in this f of x? Yeah, probably 5'10", 5'6" or something. I forget what the average height is. Okay, does that make sense? Okay, so then this leads to the first property or the first moment of a distribution, and that is the mean. Now, I'm not being mean, this is the mean. What's another word for mean? Average. Okay, I'm not saying that your average, that would be mean. I'm saying this is how you calculate the mean of a distribution. Ready? How do you do it? You got your hand ready, so I want to know how it goes.
You add up,
Excuse me.
you add all the things together, and then you divide by the number of things.
Yeah.
Okay, you add all the things together and you divide by the number of things.
Something and divide by,
Good.
Yeah.
So that is 100% correct in what circumstances?
Right.
not when it's crazy.
Not when it's crazy. What's that? Okay, so let's have a look here. For a mean, we want to know, what is the thing we want to know here?
The average?
Yeah, what does that mean? What is that?
The number.
I guess
is
at that
like-
point, the most probable.
Intellectually, yeah.
What's the middle?
Because it's from 0 to 1, is it like a 50% rate?
Okay, so we have some different ideas here, and we're gonna have to look at each one of these individually. We've heard the definition for mode, we've heard the definition for median, and I'm asking for the definition for mean.
I think they-
It's
the
the
most
only
likely
one
value
that
would
has
be
no
that.
Excuse me?
If they add the weights.
Interesting.
Think of average.
Because remember that, let's say we take the mean value of height. Is that the height that's in the middle of the distribution between 1 and 8?
No, it's 1.
No, that would be like 4 and something,
Oh, we can get it to.
because it's weighted by how many people there are, right? At each bin, at each interval. Okay, so in fact, the mean is the expectation value, right? What is the expectation value for X? So in practice, what does that look like? Well, I just said. That's how you write expectation value, E, right? And I can write this as a continuous distribution or a discrete distribution, and all I'm doing is I'm replacing g of x with x.
Question.
Yes.
Do you want us to like, I guess synonymously, compare expectation value to like the most likely outcome?
I haven't said anything about likelihood yet.
Okay,
Likelihood is itself a definition,
right.
okay? So what we're gonna do is we're gonna define two other terms, the mode and the median. And you will see that likelihood. Well, okay, you'll get there in a second. Okay.
Okay.
So this is the expectation value. I'm gonna use the word common, the most common value, as opposed to likely. Because we're gonna talk about what the word likelihood means a little bit later. Does that make sense, John? I know that seems like a stupid distinction, but it will make sense.
No, I think that makes sense. Yeah,
Okay.
thank you.
Okay. Does that look similar to what you already knew? No, it doesn't, right? Like, that's so stupid, why would you write that? That's not how I've ever done a mean in my whole life. Well, in fact, I have done a mean this way my whole life. What is the f of x for a uniform sample? What do you mean by one? So-
They're all weighted the same.
They're all weighted the same, so therefore they must sum to one. So therefore, they all have to represent a fraction of the total. So if I take, say, my die here. I take my die here, I say, how many sides are there? 6. So what's the f of x of getting any one side? 1 of 6. Good. Now let's ask the question, what is the mean value you're like to get? How do I sum this up?
And here's my one to each base.
Yeah, let's do that. Okay, so let's just walk through it just for purposes of explaining. So the first one would be 1 times 6, 1/6. And next, okay. What does that look like? Well, we can take that 1/6 right outside. And that's the sum of x, right? X equals 1, 6. That looks a lot like your mean, doesn't it? So what happened there is your probability distribution function didn't depend on x. It was a constant, it came outside. Right?
What's the one in the, I'm confused why they're not all one. Why is it going 1, 2, 3, 4, 5, 6?
So this is the value of x. And this is f of that x,
Oh, that's what you're, okay, no.
right? So what's the mean? Of a dice roll? What's the expectation value of a single dice?
1.
What? No. 12? Greater than the values that are possible on the dice?
3.
Please, let's do it now. Now you all have to do it. And ask your friend, because I have heard numbers that are larger than the possible ones. I've heard numbers that are.
I'll show you.
I got a number, but I'm not happy about it.
What number did you get, John?
3.5.
3.5, John?
I know, I don't like it.
That's right.
I also wrote it.
That's right. How did you get that, John? What is it?
I took the average.
Yeah, so that is the average. So let's think about this really well. So, John, you were talking about, is that the most likely number? Can you roll a
Right.
3 more?
No.
No,
No, it's right, so it's kind of silly when you talk about what is the likelihood there. But the most common number is 3.5. Well, it's a uniformly distributed die, doesn't tell you what the, is represents, if each one of them has equal sides, the mean is kind of useless, right? Okay.
right,
That makes sense?
yeah,
Okay. So how did you do it? Well, you could do this, you could do the whole sum, but you could also just add the edges. And you could say 1 plus 6, 7, and then you just take the average of the two. That's about. So you could go 6 plus 1, 7 plus 5, that's also 7, and then 3 plus 4 is also 7, and I did all the sums that I did. And my 3. That's the only thing you learn in grad school, how to do math like that. Okay, so the expectation value is good. Is that gonna help you in the casino? So let's do some other definitions really quickly. What other words have we heard before having to do with like mean, not standard deviation, don't get there yet.
range,
Range, okay, we're not gonna get to that today, but that's fine, we'll come back to that.
oh, okay,
Mode, I like that, and median. So what is mode?
the one that shows up the most,
Yeah, what John said.
The one that shows up the most.
One data.
like the abundance of it,
Okay, hold on, so let's dial into this idea. So we said something that is mode. Mode is the value x that shows up most. Yeah. So how do we mathematically think about that in this context that we've used so far? What's that?
I have the most weight, that's like two.
Good. Another way of saying that? Like, how would I rate that? Where's the problem? What am I pointing to?
F of X.
Where f of x is an x, right? So we might do something like this. We used that terminology before. You like draw this thing, take the derivative, set it equals to 0, find out where the peak is. Right? Okay, so that's the definition of the mode, just like you're talking. Where is it? Right? What is the top of your distribution? Okay, what's about the third one? Median. What's that mean? What? Middle. Is that true?
It's like, when you order a data set.
If it's like
smallest to
all
largest,
those,
there's like whatever data is in like the middle.
I don't.
you like
I don't
can
know.
force the middle,
Oh, of the two die.
Um,
Interesting, yeah, so let me see if I can make an analogy with the two die with median. Medians are better when you have sort of a skewed population, like the distribution of incomes in America. So if you take the average compared to the median, you're gonna get two different numbers. Unfortunately, for two die, that number overlaps because there aren't outliers. So usually what I try to give for median is the idea is if you have a distribution of a value, okay? It is where I have a value x, where x in the CDF equals half. I heard a lot of people say, what's halfway through, right? And that's almost right. Because it's not the values themselves which are at half, it's the CDF being at half. What was the CDF again? And that means,
What's the probability from the start to whatever value? Up to that point.
Okay, so if I think about that in the context here, the CDF is a half. Where have I gotten to? Half of all of the total numbers. Okay? So not just half of the range, you know, from 0 to L or something, right? However they're distributed, once I've gotten half of them, that's the median. And those don't necessarily overlap. So we can say something along the lines of the definition of the median, we'll call it M. Well, f of M equals a half. Okay. And I might also say, you may hear the word quartile. This one here, so this is the CDF here. And then this is M, we're gonna define that as median, that's the big M there. I guess it's kind of fucked because they're all big M's, but this is the only one I want to look at. Okay, so this is the CDF of M equals a half, and you can work that backwards, right? So once you set it equal to this, you can calculate where M is if I give you some function. And similarly, you could say that the first quartile or the lower quartile, so this is what does quartile mean?
25%.
Quarter, so it's the first quarter. Okay, and similarly, I could ask, what about the upper quartile? 75%, very good. Okay, so in a distribution, and this is an idealized distribution. Okay. All right. So I'm not a very good drawer, but I will attempt. Okay, so let's look at all of these. The mean is gonna be where? So hold on a second. So this is X. And this is f of X. The mean is the peak. No, the mean is not the peak. This is f of X. What is the mean?
This curve
Yeah,
is
very
mean.
good. No. You're right, but that's not what I want. I never said the mean was f of X. I heard people say it's the top. And I said, no. What is the top? The mode is the top. Because this is the maximum of f of X. Ah. Right, because you're thinking about it as the sum of the values themselves, right? It's going to be shifted to the right. So the mean is actually out here. Okay. Mean, and where is the median? Before or after?
It should be.
The middle of what? Yes, that's correct. So in fact, it's somewhere like that. Yeah, that's totally okay. I mean, we didn't do a single calculation there, right? We're reviving, right? We're saying like, okay, vibes are off because there's more stuff to the right. Right? So if I'm counting, right, here's how I want to think about it. I'm thinking about the median. I go 1, 1, 2, 2, right? And that's a joke, I'm not actually. 3, 3. So I'm necessarily not going to end up here because I have all of this long tail out to the right. Right? So means are dragged towards the extremes. Medians are less resistant to the extreme. Okay? And modes are just where the peak is. So you may say to yourself, well, what about a different distribution? Okay, so your boss We work at a Fortune 7,000 company. It's like 10 years from now. And here's your f of x, and here's your earnings report. Oh shit. Okay, so what are you gonna report here? Where's the mean? The mode's on the big one, right? The mode's right here. That one we got. That's easy. Right? So this is the mode.
The bottom of like the fridge or something like this.
Yeah, in between, like closer to the big one.
The mean is here.
Maybe.
That's it. Where's the mean? It's a little bit harder now, right? Because I didn't show how far off the tail goes. Now let's assume here that there aren't big outliers. This type of distribution here, you might say to yourself, oh, that's great, I'll just report the mode. Right? And that is basically telling me everything about the distribution. But if your distribution doesn't have a fun shape like that, then the mode may be very meaningless. Right? So when we were talking about how men and women's heights can be bimodal, you might have more men at a lower height or more women at a lower height, right? Then reporting something like the mode would be kind of silly because it represents neither of their heights, right? Whereas representing something like the mean, which is in between, would be helpful, right? And so if I wanted to report the median height, let's say I wanted to report heights, which one would I go? Mode, median, or mean? In this particular example, mean to tell you what?
You have it framed.
Yeah, that's the expectation value for x. What's the most common value for x that you're gonna get when you apply x times the probability function? Okay. Not the same as mode. Not the same as mean. Bummer? Lost anyone? Cool. More math. All right, so that was what we call the first expectation value or the first moment of the distribution. Okay. Let me show you the second moment. The variance of the distribution is going to be written like, let's see how I write it perfectly. Variance V of the x is the expectation value. So this is a specific expectation value, but I'm going to construct a funny one. Okay, you're gonna love it. Here's x minus, oh, and let's call this something meaningful. Mu, or the mean. Okay, so x minus mu, quantity squared. So we have constructed now mathematical formalism here, which does a couple different things. It says, how is x compared to the mean? Okay, so you say x compared to the mean, if this number is small, okay, cool, I don't know what that means yet. And if this is a large number, cool, I also don't know what that means yet. But it's squared, so that means I never end up with positives and negatives canceling out. So even if mu is larger than x, or x is larger than mu, it's only their difference that matters, but I'm squaring all of the values. Does that make sense? Okay. So I might construct this as something like, and I'm just gonna write both of them here, even though we'll probably only end up using one later on. Now notice this doesn't have an index on it. So in order to compute the variance, you must first calculate the mean. And the mean is a given object for your data set. That make sense? Yeah, go ahead.
Just remind me what the big X stands for.
Yeah, so this is our random variable. So if I'm thinking about, in this case, you know, the 2 die that we were rolling. Right? You could say, well, what's the mean of the 2 die that we rolled? Now that's a question.
What do you mean?
2 die. Is it 7? Yeah.
Yeah, I think it is 7. I don't like it.
So hold on, let's remember, this thing has a probability distribution function. 7 is mode. Right? 7 is the one where f of x is peaked. But the expectation value for 2 die is peaked, so it's differently weighted. Is that right? Not a lot of scratching going on. What's that?
Yeah, we have 3.5 for 1 die, so that's the expectation value for a single die.
Uh-huh. And how are the distribution functions for those two?
It was 1/6.
Okay, so here's the 2 distribution functions. Okay. So here's f of x versus x. Okay, and for one of them, it was uniform. 1/6. For the other, which one's going short? All right, well, the other one looked like this. Let's assume that I did that, but I didn't. So do we assume going into it that they give the same answer? Yes? No. All right, you can do this one, and you tell me on Wednesday, or you can tell me after class.
It's not the, like,
It's not which, this one?
like you can't get a point something on the dice.
You can't get a point something on the die, that's true. Maybe the mean is the mode. So in fact, here I do have the number 7, and it is the most probable. And
It is symmetric too.
it's symmetric too. Oh, so maybe it is still 7. I'll let you find out.
I think it was.
I think it's.
I know, but is that on vibes or did you actually do it?
Five.
I know it's on vibes, and that's good. We want both, right? We want to make sure that our own expectations work. But we also want to make sure we can always go back to the math to verify it. Because we would have said 3.5, doesn't make any fucking sense. Right? We would have said, well, 3 or 4, when the reality is it's 3.5, right? Okay, so verify this. Trust but verify. Okay, so this is your random variable. Okay,
Maybe that's why you want to. Two die. You know, like in the stuff, you have a little 1 die, right?
yeah, 1 die sucks. Because it's a very even distribution. Might as well flip 1. Right? Or flip 2 points. No, that's right. I mean, if you want to introduce a chance of randomness into a game, now dice rolling sucks. So play any game that doesn't have dice roll. Sorry.
No, have you played the game that like has instead of numbers, it has the like spade, star, and the dice that you rolled in? Have you played that one?
I played games with different dice.
Yeah.
It's really cool.
I played a zombie game.
I don't know if I could Google based on that description, but I will permit you to send me the link. Because I have a account with like a board game geek. That just shows you the level of the geek is. So we have games at the house, everything. So if it's a good game, I'll look it up. So I'm a bit of a game snob.
It's a betting game, so
It's a what?
it's a betting game. You can use your mouth to get the-
Ooh, I like betting. Love money. Okay, there's another game called, okay, wait, I can't. We're gonna come back to it. Get me too excited. So here's the variance x. So this is the variance of a random variable x. Okay, and I just said a lot of words that sound really similar. So variance means how is these random numbers distributed with respect to the mean, but agnostic to the sign. So I'm not weighting it plus or minus. Does that make sense? And this is a construction. We'll see what that means in a few seconds. Okay. Generally speaking, you can take any moment that you want. Can I get rid of this? But it's fast enough. Too exciting, more games, all right. I need that big one. Like 4 feet long.
That was.
I'm gonna go steal it.
I know, it's sensitive, but
So
What?
you're gonna see it, so.
there's something funny that. Never lets me see that.
Okay, so we can sometimes talk about moments. Oh, like that.
Yeah, that's.
Moments. So moments are defined like this. Mu k is defined as the expectation value of x. K. The fuck did I say? Okay, so I said, here's the discrete random variable. And k is some power of that discrete random variable, or sorry, not discrete, of that random variable. And it can be for either. And so I could write this, like that. Sigma sum, and you're just gonna go xk, xk. Right? And I'm gonna forget the indices for a second because I want to show you something really cool. So let's look at this for one moment. This is the variance of x. And we can write this in terms of the expectation value. Okay, that's the expectation value of x minus mu. You'll notice that mu is the first moment. So x to the 1. Right? And you'll notice out here, this is still mu. Mu to the 1 would be the mean for the first moment. Right? Okay, this quantity squared. So this will be a form of a second mode, so let's look at that in a second. So let's write this out. What do I get inside of my expectation value? Very good. Thank you so much. Okay, and so let's only apply the expectation value to the things that have the ability to vary. So for example, the expectation value of a constant would be. What would you expect 4 to be? 4, very good, okay. So if you have something that can vary, you can say expectation value, but if you have a number that is fixed, like the mean of a distribution, it is that number. So we can apply this out. We say the expectation value of x squared minus 2 mu, the expectation value of x plus mu squared, right? And what's this?
That's me.
That's the mean. That's the expectation value, right? So let's write this again. That's the expectation value of x squared is equal to, oops, sorry, minus 2 mu squared plus mu squared. Oh, interesting, interesting. So I can write this as e of x squared minus, oh god. And that is the definition. of Variance. Okay. You may also see this as any questions about this? Okay. Sorry that you didn't get to make more money today. I'll see you Wednesday.
So no class, we don't want to.
You can come, I just won't be here. I'm in Colorado.
Okay.
So we actually did double our money today if we won.
Uh,
We bet.
some of you did, yeah. I think-
Okay.
Yeah, if
And
you
then-
go off vibes, then you.
And then she got $9 back for betting and drawing the 10. Which is a one.
A double, actually, yeah, double my.
It all works out.
Yeah.
Like, minus 10.
No, I actually have $9, I just say I have $1.
See it.
My heart is.
Okay, bye now.